Hi, my name is Dr. Cinzia Casiraghi, and we are here at the National Graphene Institute in Manchester. This is the Raman room, and today I'm going to show you how to take a Raman spectrum. Usually we measure in the dark because the detector is very sensitive, but today, just to make things easy for the camera, we are going to do the measurements with the light. When you want to do a Raman experiment, you need three components. So first of all, you need a source of light. So typically you use a laser. So here we have 4 lasers. So we have different excitation lines from UV to infrared. So this allows us to do multi-wavelength Raman spectroscopy, which is extremely important in characterizing graphene and in general any carbon nanostructure. The second component is the spectrometer. You can see indeed that here the laser beam is sent inside this box, which then sends the laser inside the Raman spectrometer. And finally, the third component is the optical microscope. The second component of the Raman spectrometer is this box that you can see here. So the first component is the laser, and then in this box there are the optics and the filters that you need to do Raman spectroscopy. So your laser is coming from the back, from this side, and then here you have different pieces of optics. So the laser actually gets scattered from this corner to this corner, and then up here. And this is a very important area of the spectrometer, because here you have basically a filter. So 50% of the laser beam that is coming from the bottom gets sent to the microscope, which is this other side here. But this filter is also able to transmit 50% of the light, which is the light that you will detect in a Raman scattering experiment. So your 50% of the light goes inside the microscope, and then it gets focused here. And so typically when you do Raman scattering measurements, you measure in backscattering geometry. So it means that you detect the light that is scattered in backscattering, so at 800 degrees. So your scattered light will go back inside your microscope and then goes back to the filter. And here your scattered light will go through the filter, will be transmitted to the filter, and it will be able to reach this other side of the spectrometer where we have the detector, the CCD camera. And before reaching the CCD camera, there is a filter here, typically an edge filter. There are different types of filters, but typically an edge filter which cuts the excitation line, because in our Raman experiments we don't want to measure the elastically scattered light, so the incident light, but the scattered light, which has a slightly different, inelastically scattered light, which has a slightly different energy compared to the incident light. Okay, so here we have a sample. So it's a piece of silicon with some graphene on it. And in this case, we know already where is the graphene, so it's going to be quite easy to find the flake and to do Raman spectroscopy. But in most cases, you have no clue where is the graphene, and you will spend some time looking for it under the microscope. So the first thing we have to do is to get the sample and put it under the microscope. So like that. So as I said, we know more or less where is the graphene, so I can place it already in the right position. Yep. And so here you can see the optical picture from the microscope, and this is silver contact that we place it on the sample, because now we know we can use it as a marker to find graphene, and graphene is somewhere here next to this flake. And now we are focusing with a 5x objective, so it's a quite large area. And when you do Raman, you want to use a high magnification objective typically, because these decrease the size of your laser spot and also allow you to have more power on your sample. So the next step is actually to change the objective. So now we have the 5x, so we can rotate here, being very careful not to touch the sample. We can go to the 20x, and now we need to adjust the focus a little bit. So now it's a little bit better, and we need to now look for our reference flake. And here, I hope you can see, there is already something here that looks like graphene, because the weaker the contrast and the thinner the flake. So here we have an area with a very, very weak contrast, so possibly this could be graphene. So we go around this area, and now we change objective again. So now I'm using a 20 times magnification, and now I go to 50. And again, I need to focus a little bit. And now I can clearly see a big flake here, and also some darker area which are thicker flakes. And if you want, you can also play with the luminosity, so you can make it a little bit darker. Now you can see the edges of the flake, and sometimes it's also useful to kind of close the diaphragm like that. That's the aperture on the microscope, sometimes give you better contrast. So now we click on the spot where we want to take a Raman spectrum, and we are ready. Okay, so in order to take the measurement, you need to press on measurement, new, and spectral acquisition, and then you need to tell to the Raman spectrometer the parameters that you want to use. So for these particular measurements, I prefer to use the extended modality here, which allow to take a Raman spectrum in a quite large energy range. So for graphene, we can, for example, start from 1300 and stop at 3000. So in this case, we can take all first order, second order Raman spectra, and the other parameters are related to the laser. So that's the excitation wavelength we are using, and that's the grating that give us the resolution of our Raman spectrometer. So these two parameters we don't change. Then we press on acquisition, and typically the Raman spectrum of graphene is quite strong, at least on silicon, so 10 seconds are enough for our sample. And for accumulations, typically we use 3 times, but to make things quite quickly, and we use just 1 in this case. Okay, so we press apply. We may decrease the laser power a little bit, so we can place a filter of 50%, apply, okay, and then we press run. And now the optics inside is adjusting, so it takes a few seconds, and then we should be able to see the Raman spectrum coming out. So we can make it a little bit bigger here. So here, the Raman spectrum of graphene that we just measured. So if we start from the high energy, so we see this first peak here. This is called 2D peak. It's called 2D peak because it's a second order, it's an overtone in particular, and it's a very important peak because it allows us to identify graphene. Indeed, the shape of this peak is changing with the number of layers, and every time you have a single layer, so you have graphene, you will always see a single and sharp peak. And when the thickness changes, then the shape of this peak is changing quite strongly, and this allows you to identify graphene and makes Raman spectroscopy the most used technique for identification of graphene. The second important feature in the Raman spectrum is given by this peak here. This is called G peak. It's called G because it was first discovered in graphite, and this is associated to a double degenerate stretching mode of the carbon atoms in sp2 configuration. So it means that it's typical of graphite, but of any carbon-based material where the carbon atoms have sp2 hybridization.